Hi everybody, my name's Chris Collison and we're going to continue today with quantum mechanics, CHMP 442. This is going to be lecture 8 and I'm going to jump into a quick review of lecture 7 and talk about what we'll cover in today's class, and then we'll jump into the PowerPoint and we'll go through some of the math that explains some of the new quantum mechanics associated with particle in a box. So without further ado, let's jump straight in. So here we go. This is lecture 8. And so we'll start with this review of lecture 7. And in lecture 7, we basically said how the Schrödinger equation was developed. And we took a classical one-dimensional wave equation, and we applied that with a standard general solution. We applied the de Broglie matter wave to that, and that's how the Schrödinger equation came about. We talked about operators, and I introduced linear operators, commutative operators, and also non-commutative operators. I told you how you would measure something called the commutator, which would be 0 if we have a commutative pair of operators. Why was this important? Well, non-commutative operators, when multiplied together, give us a constant, and basically that tells us that the order in which we operate on a function is going to impact the answer from those pair of operators operating. In other words, we are needing non-commutative operators because that mathematically describes the Heisenberg uncertainty principle. So we looked at a couple of eigenvalue problems. I talked to you about how the wave function squared is interpreted to be the probability density, and then we started very briefly to look at the particle in a box. And so that takes us on to today's class, because we're going to continue thinking about the particle in a box, and we're going to introduce some boundary conditions. And it's those boundary conditions that lead us to quantized energy. So I'll demonstrate that in today's class. We'll look at some solutions for the particle in the box, and we'll apply this particle in a box approach to a real-world example with butadiene. Okay, so there's our butadiene molecule. I'll talk to you about normalization, and it ends up being another boundary condition that helps us determine an exact solution to the Schrödinger equation. And then if we have time, I'll talk about the correspondence principle and also the particle in a three-dimensional box. So that's the sort of 2-minute introduction to what we're doing today. Let's jump in and take a deeper dive. So this is where we left off in the last lecture, and we have our Schrödinger equation in here, and we've applied it to a wave function psi, and we've got a suggested wave function in here that is psi of x equals minus a cosine kx plus b sine kx. When we plug that in, we saw this in the last session in lecture 7. We do end up getting a solution. We do end up getting a constant for e. It's not a function of x. And we talked about how really at the moment we can have a and b take on any values that we want, and even k is not quantized at this point. So k is not quantized, and e is not quantized, right? So I think actually that's the main point. E is not quantized because k can take on any particular value. Here was the particle in the box scenario, and we introduced this, and we said that the potential at the top here, so when outside of this region of x equals 0 and x equals a, the potential is infinity. So that means it's like we have an infinitely high cliff and that ball just can't get out. And we're also going to say that the potential inside the box is equal to 0. So we've got these boundary conditions. So what we now need to do is apply these boundary conditions to our solution. And so we recognize the importance of probability, and we said that the wave function squared, or more importantly, in fact, the complex conjugate of the wave function multiplied by the wave function, that ends up being the probability density. And so at some point, as soon as we've reached this point where x equals a, the probability of that electron being at that position must be 0, because at that point the potential goes to infinity. So we know that that electron is not outside the box. At the same point, when x is equal to 0, the probability must also be 0. So we kind of have to recognize that the only way we're going to get 0 probability is when psi itself ends up being 0 at these positions. So psi of x, we can actually, let's write this a slightly different way. Let's say that psi of 0 must be equal to psi of a, which must be equal to 0. And so this gives us, when we apply this boundary condition, it allows us to say, well, what are the conditions? Let's plug, for example, psi of 0. Let's plug that into our expression here. So that is minus a cosine k times x, which is 0. Okay, so k times x is equal to 0, plus b sine, again, k times x is going to be equal to 0. All right, so we know that the sine of 0 is in fact 0. So this term goes away. Cosine of 0, of course, is plus 1. So the only way that we can have psi of 0 be equal to 0 is when a itself is equal to 0. So this allows us to simplify our solution. So now we know that our solution has to be, well, a is 0, so this term ends up going away up here. So we now know that we end up having a solution that is psi of x is equal to b sine kx. Okay, so now the next thing is we have to think about, well, what happens when x is equal to a? So now we've got a slightly different situation. So we know the psi of a must be equal to 0, so which is equal to b sine ka. So now we have to ask ourselves, well, when is sine ka 0? Of course, we can also say, by the way, that, you know, b could be equal to 0, but if b is equal to 0, then psi is equal to 0. It's basically what we would call the trivial solution. So we're not going to spend too much time over that, but I'm going to recognize it nevertheless. But the better solution here is to consider that really we also can get a value for 0 when the sine of Ka equals the sine of n pi. Okay, that's also a condition where we will end up getting a 0 value. So this now tells us that K must be, in fact, equal, or Ka is equal to n pi, so K is equal to n pi over A. And that leaves us with a new improved solution to this expression. So in fact, what we would end up doing is we're going to replace the K in here in our solution with n pi over A. Let me write that on a new slide. So let's write this solution down once again. Okay, so we have, now we understand our final solution. Psi of x is equal to b sine n pi x over A. And we also have to recognize that n is now an integer, because only when n is an integer can this expression be equal to 0 when x is equal to A. We're also going to note that K, right, we said this before, is equal to n pi over A. Well, we expressed that. That was part of our solution. That was the way that the boundary conditions meant that we have to say this. But we also, from before, remember, we have K being equal to 2m e to the half over h bar. So, of course, we also recognize that h bar is equal to h over 2 pi. So let's put the 2 pi in here along with 2m e to the half, and we're now going to leave h in the denominator. So let's now solve. So we're going to use this part of the equation and this part of the equation, and we're going to square both of these terms, right? So now we're left with n squared pi squared over a squared is equal to, and then up here we got 4 pi squared. We're going to square everything, multiplied now by 2me over h squared. Solving for e, okay, we now end up with e equals, we're going to cancel the pi squareds, so e is equal to n squared h squared, and that is over, so 4 times 2 is 8, so 4 times 2 is 8 m a squared. Okay, so now we've actually quantized our energies because of the boundary conditions that led to this integer n being included because of this pi term up here. So n is equal to 1, 2, 3, and so on. So the point here is that now the energy has discrete values. And we're going to say that n is, because it leads to these quantized discrete values, we're going to say n is a quantum number. So let's take a look at some of these functions. Okay, so I'm going to draw on the left-hand side of the screen here a box. And we've got x is equal to 0 and x is equal to a in this box. And what we're going to do is start to think about the wave function as a function of n. So, for example, psi 1 is equal to b sine, well, n is equal to 1, so the n becomes 1, so it's sine pi x over a. We've also got, actually let's draw on the right hand side here another box, and on this box on the right hand side we're going to draw in fact the probability density. So we're going to imagine squaring these, because remember our probability density is psi star of x times psi over x. So in this particular case, since we're not dealing with any complex numbers, it's really just psi squared. So we're going to look at these functions on the left hand side here, and we're going to say what happens when we square those values. So of course, when we square the value, we're just going to get a kind of steeper quadratic, if you will. But we can look at the shapes, and we see how these shapes evolve as we change the wave function. So psi 2 in here is equal to b sine 2 pi x over a, and a wave function there. Of course, it has a node in here. We saw that in chapter 2 when we were looking at solutions to a wave equation for a string, a standing wave for a string. So that's psi 2 in here. If we look at the probability density here, though, what we're now going to recognize is we've got some probability density that's ends up being this double hump, if you will. Let's have a look now at psi 3 is equal to b sine 3 pi x over a. So now we've got an expression that looks something like this. What does the probability density look like? Looks like so. We can also write this, by the way, as shown. And lastly, I mean these keep going, for example, but you get the picture. Psi 4 equals b sine 4 pi x over a. And it looks something like that. It's pretty difficult. And there's our probability graph in here. So the important thing is that we've got n equals 4 here, n equals 3, n equals 2, and n equals 1. And we're also going to say, well, what's the energy for each of these particular cases? So let's have a look at those energies. And here we can say E is equal to 16h squared over 8ma, and E is equal to, it's going to be 9h squared over 8ma. Sorry, that's ma squared. Here we've got E is equal to 4h squared over 8ma squared, and the last one here, E, this will be E1, E2, E3, E4 is equal to 1h squared over 8ma squared. So these are the energy levels and the wave functions and the probability densities for the particle in the one-dimensional box. Good to recognize these figures and to see how those graphs represent the functions and also represent the squares of those functions. We'll come back and look at these and reflect on this in a little while. Let's look at a real-world example. So as I mentioned earlier, we're going to consider a real-world example that involves the molecule butadiene. And when we think about this particular molecule, we have these pi electrons, these sp2 hybridized carbons, and these pi orbitals, these p orbitals actually stick out, and so they're conjugated across that molecule. What else can we say about this molecule? Well, we assume actually in this particular case that the molecule is linear. It's not, it is slightly bent, but we're going to assume it to be linear for this model because really we're thinking about this particle in a box, right? So we'll say assume to be linear. And we need to determine the length, and the length we can kind of look this up because we know what a carbon-carbon bond length is. There's two of them, so because there's two of them here and here, the length of those bonds is 135 picometers. And we've also got this carbon-carbon bond, single bond in the middle. So one of those is 154 picometers. And we've got, I guess we can think about carbons on either end in here. And so we actually have to consider, we've got half a carbon at each end. So we're going to say half of the carbon atomic radius at each end. So at each end there's two ends multiplied by 2. So when we plug that all in together, this is actually 77.0 picometers. So we add this all together 2 times 135, 1 times 154, and 2 times 77. And then we end up with 578 picometers. And so what we're going to now say is this is our value for A in here. So here's our box. Okay, so A is equal to 578 picometers. Well, if you go back to general chemistry, we're going to just pull from general chemistry now. We're going to say, well, there's the Pauli exclusion principle. And this basically tells us that each state can hold 2 electrons. Okay, so what we're going to start to think about, here's our molecule. We've got a ground state in here, and we're going to have n equals 1 and n equals 2, because this is going to follow the same kind of graph that we drew in the previous slide. But we're going to say there's 2 electrons, and we're going to show an electron as a little arrow up or down. This is associated with spin. We'll come to that later in the course. But we're going to say that our ground state is with 2 electrons in n equals 1 and with 2 electrons in n equals 2. We're then going to consider our first excited state. So here's our ground state. And then we're going to consider our first excited state. And what does that mean? Well, we're going to take an electron from n equals 2 and put it up into n equals 3. So this is going to be our first excited state. So now we're going to ask, what is the transition energy? Let's change color here. Okay, so delta E, okay, looking at the previous graphs, we're going from n equals 3, so that's 9h squared over 8ma squared, minus, so we're going from n equals 3 up here to n is equal to 2 down here, so that's going to be minus 4h squared over 8ma squared. And of course, that ends up being a value of, well, 9 minus 4 is 5. So the answer is 5h squared over 8ma squared. Of course, we know the mass of an electron. We know what A is in this particular case. And the answer comes out to be 9.02 times 10 to the negative 19 joules. Okay, 9.02 times 10 to the negative 19 joules. That's equal to h nu, which is equal to hc over lambda. A couple of things to throw in here, by the way. Energy, look at your simple physics, is equal to the charge times the voltage, and a unit of energy, therefore, is going to be fundamental charge, E, times 1 volt. So this is called an electron volt. Okay, and 1 electron volt, by the way, is equal to, well, is that fundamental charge 1.60218 times 10 to the negative 19, and that's coulombs, multiplied by 1 volt, and that ends up being equal to 1.60218 times 10 to the negative 19 joules. So often when we're talking about photons, we're going to think about electron volts, because we're talking about the energy inside an individual photon. And most of the time when we're working with joules, we're thinking about things on the macroscopic scale. So what we're going to do is just convert now for a second 9.02 times 10 to the negative 19 joules. We're going to convert that into wavelength. So again, we remember up here, we can do this. So I'll let you do the simple algebra in here, but this ends up giving us a value of 220.6 nanometers. This is in the UV range. Or, and test this out for yourself, this is 5.63 electron volts. And the point here is that we typically measure electronic transitions in the ultraviolet range or the visible range, and you'll do something similar in your physical chemistry lab, where you're actually going to use this approach to compare the theoretical answer with a measured experimental value. And you'll see that most of the time with these organic molecules, with pi conjugation, we see absorbance in the ultraviolet range. So that was our real world kind of case in here. Let's go back to red here for a second and come back and tie up a loose end, because really we haven't yet talked about B. So what about B? And so then we say, well, okay, remember our wave function was equal to B sine kx, but we haven't yet specified B. So what are we going to do? And this leads us onto another section. So now we're up to section 3.6 of the textbook. We're basically saying here that wave functions must be normalized. But what do I mean by this? What do I mean by normalization? It's something that's absolutely critical in quantum mechanics. It's another form of applying a boundary condition. So let's have a look at that in the next slide. So, wave functions must be normalized. So, Max Born puts forward this idea that psi n star, so that's the complex conjugate, multiplied by psi n. We must have the complex conjugate in there because the wave function may be a complex number, but the probability density must be a real number. So we'll come back to that. But Max Born says that this is the probability. So this combination along with dx in here is the probability. We're later going to go on to say, by the way, that psi star n in 3 dimensions, x, y, and z. So in other words, over a volume multiplied by psi of n x as a function. That's a function of x, y, and z multiplied by dx, dy, dz. So this ends up being our probability density in here. So here's our probability density. And what we have, dx, dy, dz, is a volume element. And really, when we think about this, a probability density multiplied by a volume, well, that's kind of like saying mass density multiplied by a volume. Well, what's density times volume? Well, it's equal to a mass, right? So, but we've got probability density times volume. That, by comparison, is actually going to be a probability. So what we're trying to do now is basically say, listen, what we care about is this probability piece in here, and we're going to normalize, we're going to add this boundary condition because we know that the particle in this particular case is in the box, right? We know that there's no possibility that that particle can be outside of the box at a potential of infinity. So we know it's in the box, so we can use probability to help us here, and this is the normalization condition. So we're going to say that psi star n of x, lots of rewriting here, right? Dx from our solution that we've just come up with is b star b sine squared n pi x over a. We don't know what b is yet, right? So it could be a complex number. So we're going to assume it's a complex number for the time being. Let's talk about this for a second. Here's our complex conjugate. And this is in math chapter B, by the way. So let's just remind ourselves that when we have a plus bi, here's our complex number. The complex conjugate is the same number. We're going to replace the plus with a minus. And when we multiply the complex number with the complex conjugate, what do we get? Well, we're going to get a squared in here plus bai minus bai plus b squared. So these terms in the middle cancel, and we end up with a real number, a squared plus b squared. And that's the key here. We need to end up with a real number because this is a probability, right? So this in here must be a probability, and a probability must be a real number. So that's why we have to use complex conjugates. So probability is real. Probability is real. Okay. Furthermore, we're also going to say, where is the electron? So, we remind ourselves, well, where is the electron? It's in the box. Okay, so because it's in the box, we also know that the probability for it being in the box, because there's no other possibility, that probability must be equal to 1. So that's something we'd call a completely certain event when P is equal to 1 and that electron is inside the box. So this ends up now being another boundary condition that we can use. So rewriting an expression of Max Born's description of probability, we're basically saying that if we have this box, right, and with V being equal to infinity, the potential being equal to infinity outside the box, well, we know therefore that the electron is inside the box, somewhere between x equals 0 and x equals a. So this is where we select the limits in our integral, and we recognize that because the electron must be in the box and it is an absolute certainty, we basically state that's equal to 0. So what else can we write? We can also write this in a different way, right? So we can substitute for our b, and here's our integral a and 0, and sine squared n pi x over a dx, and we know that that now is equal to 1. So what does this allow us to do? It actually allows us to solve this expression now so that we can identify what this constant b is. The constant b might be a complex number, by the way, so that's why we have to include the star there for the b. So how are we going to solve this, right? We're over the next slide, we're going to solve this expression. Let's see how we do that. What we're also going to do is say, well, we know that we're going to let's say let n pi x over a, we're going to let that be equal to z. Okay, and so, oh, by the way, let's just move this around a little bit. What is x equal to, therefore? X is equal to a times z over n pi. What else can we do in here? Oh, we can also write down dz by dx now. So dz by dx, we're just taking the derivative of the expression on the left hand side, so that ends up being equal to n pi over a. So of course that means that dx is equal to a over n pi dz. Okay, so that'll become important because later we're going to substitute for dx in our integral up here. Lastly, we're also going to say, well, because we've got our integral here, when x, so let's say at x equals a, z equals n pi. Okay, because of course when x is equal to a in here, these will cancel, and that will leave us with z equals n pi. So what we're now going to do with all this is we're going to substitute and move from this expression. Let's substitute, let's actually substitute right here. We'll substitute for the a. We know that that's going to be equal to n pi now as our limit, and 0 down here. So these are our new limits. We're going to have our sine squared. This is z now, right? So z is this expression. So sine squared z, and then we've got to replace the dx. Well, dx is a over. So that becomes a over n pi dz. And of course, right now what we're doing, by the way, is we're only solving for this integral. So let's solve for this integral, and when we solve for that integral, then we can determine what b is, and so this ends up now becoming equal to, well, let's bring the a over n pi outside of the integral, n pi over 0 sine squared z dz. Okay, how are we going to do that? So this is also another example of where we're going to use a trigonometric identity to help us. So let's use a trig identity. And many of these can be found at the front of your textbook, but it's also good to pull down a list from online. But what we've got is sine squared z equals 1 minus cosine 2z over 2. So we're going to substitute that now into our integral. And by the way, that when we substitute for sine squared z, the 2 is going to come outside of the integral. So now we're going to be left with a over 2 n pi. So we've pulled that 2 outside. Let's remember our limits, n pi and 0. And inside the integral, we've got 1 minus cosine 2z dz. In that integral, let's solve that right now. Actually, let's split it up. So a over 2 n pi, and then we've got an integral of n pi 0 1 dz minus a over 2 n pi integral with the limits here of cosine 2z dz. So those integrals are pretty straightforward. So what do we end up with? So we end up with a over 2 n pi, and z is the integral of this piece. So I'm going through this really slow at the moment, and this will speed up as we go further through the course, as we become more familiar with the math that we've probably forgotten about some time ago. So, and the integral of cosine 2z is going to be sine 2z and over 2, and the limits here n pi and 0. Of course, there'd be plus some constant, so for integral, but this comes out to be, well, nz becoming n pi minus 0. Well, that becomes this piece here goes to a over 2, and then when we plug, by the way, n pi in here, so sine of 2 n pi, well, that's 0 as well. So it turns out that this expression here totally goes to 0. So a over 2 minus 0, And so the answer here is a over 2. So in other words, it's not a function of v, of z rather, and therefore it's also not a function of x. And that's pleasing to us, because ultimately the integral that we started with, right, this b star b integral a to 0 over sine squared n pi x over a dx equals 1, well, that simply becomes now b star times b times a over 2 is equal to 1. And so let's now move forward to the next slide. So we now recognize from that b is equal to 2 over a. That's the square root of 2 over a, basically. And so our final expression for the wave function, psi n of x, so we put the n in there because it depends on that quantum number, but we end up with 2 over a to the half sine n pi x over a, and that's for 0 is less than or equal to x, which is less than or equal to a, and n is equal to 1, 2, 3, etc. Okay, so here is our solved wave function, and note that we've used the boundary condition that's associated with something we called normalization. So we've used this normalization. So we've used this normalization to find what we will call a normalization constant, or you know, we've identified what that constant b can be. I'm going to say that this is a normalized wave function. So this is a normalized wave function. There's a subtlety that comes in here that will come back later, because actually the solution still works with b taking any value, right? So I'm going to write here, but can b be any value? And still we have an eigenfunction? And the answer is actually yes. And this is because the quantum mechanical operators are linear. And what this means is that any operator operating on C1 F1 of x plus C2 F2 of x is equal to C1 A hat F1 of x plus C2 A hat F2 of x. And this will become important later when we look at superpositions or additions of different orbitals in order to understand the total energy, perhaps, of an atom that contains many electrons. Okay, next up, we're going to talk very briefly about the correspondence principle. And I'm going to say, let's imagine a classical particle that's bouncing backwards and forwards in this box, okay? And we can break our box down into sections, into quarters, and we might say, you know, what's the probability of finding that particle in this spot? And it turns out that we recognize that the probability of finding it there is the same as the probability of finding it in any quarter segment of our box, and the answer is going to be 1/4. So this is a classical particle. But what happens now with quantum mechanics? So here we have our box, and as you'll recall, when we think about the different energy levels, or the different psi1, here's our let's look at the probability when n is equal to 1, right? So we have this probability function that says that there's actually a large chance, a much larger chance, in fact, if we look at the area underneath this curve, there's a much larger chance of finding the electron in quadrant 3, for example, compared to quadrant 4. So the probability really is largest there in the middle. Now, as we go to higher quantum numbers, we recognize that the probability of finding the particle in the fourth quadrant actually ends up being the same as the probability of finding it in any other section of the box. And in fact, actually, let's sort of extrapolate to maybe n is equal to 16, right? N is equal to 16. Would have 15 nodes. This is going to be a pain to draw. And what we find with n is equal to 16, and this would be psi 16 squared, we pretty much find that the probability starts to become more evenly distributed over the length of the box. So we can keep going, right? So we can keep going up to n is equal to infinity. And this really is a recognition of the correspondence principle. So let me kind of tie this all together and basically say that as n tends towards infinity, the probability density becomes more uniform as n increases. So here's the correspondence principle. That quantum mechanical and classical results tend to agree in the limit of large quantum numbers. Okay, so that's the correspondence principle, and that finishes this particular part of the presentation. Let's put forward a final note. Okay, so we have this solution and we have an associated energy that comes from solving the Schrödinger equation with our solution. We've just been talking about the correspondence principle, which talks us through how we get closer to a classical case when n tends to infinity. But what I want to do for a second is just think about the quantization of energy. So with quantization of energy, with these very small masses and very small box lengths, we find that there is this very distinct gap, and the particle can only take energies, discrete energies, as described by this expression. But for a second here, what happens when we imagine that A gets to be really large? And maybe it tends towards infinity, but maybe it tends towards, you know, the real world perspective. So maybe what happens when A tends towards a distance that's meters? You know, what happens if we have a tennis ball bouncing backwards and forwards inside a tennis court? Well, what we can recognize here is that this A is in the denominator, and as that A gets really large, well, actually, as it stops being really small, what happens is these energy levels start to sit right on top of each other. So the gap, right, the delta E between energy levels is equal to n1 squared h squared over 8ma squared minus, let's call this n2 down here, minus n1 squared h squared over 8ma squared. So it's maybe the gap that we care about, but the gap will end up being really h squared over 8ma squared multiplied by, you know, ny squared minus nx squared in here. So the gap is also determined by the length of the box A, so this distance A, and also the mass of the particle. So if we have a very large length of the box, we're going to find that these states start to really overlap with each other. And what we find here is that as A increases, we tend towards more of a continuum of energies. And so if you think about a ball that's moving backwards and forwards in a tennis court, that ball can take on any kinetic energy that it wants, right? And that's because of the size of the tennis court. But not only that, it's also associated with the size or the mass of the tennis ball. So think about the mass of a tennis ball compared to the mass of an electron. So this is one takeaway from particle in a box treatment. We basically recognize that quantum mechanics works really well. So quantum mechanics works well when the lengths, the features, the dimensions are about that of sort of atomic distances. And it also works well, so quantum mechanics also works well when the mass is similar to that of maybe the mass of a proton, and certainly the mass of an electron. And that's when quantum mechanics works well. Quantum mechanics does also work with tennis balls and tennis courts, but we don't need to use quantum mechanics because we're in this world of a continuum, the world that we typically already know and is described well with classical mechanics. So that's the final point I'm going to put on today's lecture, lecture 8, and we'll explore a little bit more in lecture 9 what happens when we expand this one-dimensional particle in a box into a three-dimensional particle in a box. So thanks for listening.